So let's get started. Hello, everyone. Welcome to stay here for the last, but may not be the least session for this conference. So this actually is an introductory talk about how to use the shared GPU in Kubernetes clustering using the technology of virtual GPU. It's very basic, but we hope that the idea we introduce here will be inspire you for more complicated work later. So first of all, let me introduce ourselves. So my name is Henry Zhang. I'm the technical director of VMware China R&D. I'm based in Beijing. We are based in Beijing. I'm the original creator of Project Harbor, the Cloud Native Registry project, which is already a CNCF incubation project last year. And my daily job is for the incubating new project in the emerging technology like container, cloud natives, and also AI, and all kind of stuff like blockchain and stuff. And today with me is my colleague, Yang.
Hi, I'm Yang, and I'm also from China, VMware China R&D team. And before I joined Kubernetes, I worked for the OpenStack, and I'm focusing on the neutron component. So glad to see you guys here. You know, it's the last session today, and also the last session for KubeCon Europe this year. So nice to meet you.
Okay, so let's get started with the content. So you know, there's been quite a few waves about the AI up and down in the industry last couple decades. About two decades ago, I was in the university that my professor told me that we were in the era of AI. And it turned out that that's so real, not so realistic when we were not quite there yet. But most recently, that we feel that this AI is very closer to our daily lives, and we have many applications that we can feel and touch in our daily work and life. So AI promise bring us many benefits, like the reducing human effort, boost the productivity and cost, and so on, right? Here's just some concept about AI. I'm not going to too deep into it, but generally speaking, in the AI space, we have three key elements in order to succeed. The first one is the data for training the models. The second one is the algorithm to construct the models. The third one is the computing power to create the models. So with the proliferation of internet, we have a huge amount of data already. With the advancement of computing science research, we have a new algorithm for the training. Today, our talk will focus on the third element of computing power using GPU, or especially for the machine learning workload on Kubernetes. So I'm sure many of you have listened to many talks in this conference about many use cases of Kubernetes. One of the use cases for machine learning is the machine learning workload on Kubernetes. So many machine learning workloads can be encapsulated in or run as containers, like for the portability or the manageability benefit. So running machine learning workload on Kubernetes could be a very good fit for this kind of workload, because Kubernetes right now is the de facto standard for containerized application. For example, some users may have models. So one of the benefits is that some of the users told us that many users, they may have vendors generating or creating models for them. And all these vendors need to play in the same pipeline of their machine learning workload. So need to put their workload into the same platform. So Kubernetes could be their natural choice, because once the machine learning trained model can be run on Kubernetes, it can become a standard platform for them to integrate together. So Kubernetes could be a very standardized platform for this machine learning workload, and it's ubiquitously available. It means that Kubernetes is kind of service of Kubernetes, a commodity provided by many cloud service providers. So in order to use the machine learning workload in the Kubernetes, that we need to take advantage of the device plugin of the Kubernetes in order to consume the compute accelerators, for example, like the GPU, FPGA, or ASIC. The idea is simple. I think it's a very standard document there in the Kubernetes. However, there's some limitation for the GPU scheduling in Kubernetes. The first one is the exclusive assignment, which means that once you assign a GPU resource to a particular port, you can no longer be assigned to other ports. That means that you cannot share. And the other restriction or limitation is that there's no fractional assignment. For example, in CPU, you can have 0.0 or 0.3 or 0.5 resource assigned to a port. But in GPU, you can only have the whole number, 1, 2, 3, something like that. So that would create some kind of limitation or not flexibility in the usual application situation. So I also in the community, we're seeing that there's a lot of people trying to work around with this limitation. One of the workaround is called model stuffing. The idea is to put all kinds of models into a big container to encapsulate all the kind of training models, and then you share it so that it can be run on Kubernetes to share the same CPU, same GPU. So you're seeing that there's a lot of requests or requirement for sharing GPU in the Kubernetes platform, the community. So sharing the GPU can help us to increase utilization and have the flexibility, but there's not so satisfied solution so far. There's some existing solution that we see in the community. They may have partially solved the problem by sharing the GPU resource across different workload, different pods. But one restriction is that they don't have isolation or no QoS guarantee. That means that your workload may be affecting each other, or called the noisy neighbor problem. So our solution here is trying to using a techniques called virtual GPU to help us to address these issues. So the GPU virtualization is not something new. It's just similar to the CPU virtualization. So I think many of you are familiar with the CPU virtualizations, like virtual machine, right? So in virtual machine, you can separate your CPU, and that's used by different workloads, different users. And in GPU, we can have virtualizations. Right now, there are many different vendors providing such a mechanism for the virtualization of GPU, like NVIDIA, AMD, and Intel. And sharing GPU between VMs so that you can get isolation, you can get QoS ready for all this workload. And in terms of hypervisor, the mainstream hypervisors like vSphere, KVM, and ZenServer, they all have the support for the GPU virtualization. So so I'm going to talk about this, how we can make use of this virtualization in our Kubernetes so that we can share the machine learning workload with the GPUs. And in this example, I'm going to use the vSphere and the NVIDIA GPU in our demo or for illustration purpose. So here's just a diagram showing that in vSphere, how a physical GPU can be split into a smaller logical unit called vGPU and mapped into actual virtual machines. So each VM has one or more GPUs devices and can use them as a native GPU. So that any workload inside this GPU, inside this VM, we can use this vGPU as a GPU that you can see in the physical machine. Here's the configuration UI. Basically, a physical GPU can be divided into a fixed frame buffer and used by different vGPU. For example, a physical GPU with 16 GB memory can be split into 4 virtual GPU, each have 1 GB memory, or 2 vGPU each with 8 GB memory. The compute engine of the GPU actually is shared between the vGPUs. So there's a few scheduling strategies available to fit different scenarios. Like here, I listed a few, like best effort, fixed share, and equal share. So in short, the memory of the vGPUs are fixed to each of the vGPU, but the compute engine is shareable between different vGPUs. In this vSphere console, you can see that we can choose different profile. It's called, in this example, you can see this Grid P100 GPU, physical GPU, having the 8Q, means that 8 GB memory. So by choosing different profile, you can virtually create different type of size of the GPU. And some people may worry about the overhead of virtual GPU. Here's some research we did, VMware did a while ago, studying for the the overhead of the vGPU. Actually, it's quite trivial. Like here, it is an NLP dataset, the PTP dataset, using the RNN for the NLP training. It's only about 4% overhead is observed. So virtually, it's nothing. So we don't need to worry about too much about the overhead. Now it comes to the part that how we can set up a Kubernetes cluster for GPU sharing. Before that, I introduced the basic of GPU, and then here is the diagram that we have where we can set it up. So first, the hypervisor is configured with virtual GPU. And next, we create VM using the virtual GPU provided by the hypervisor. And then the machine learning application inside each of the VM can make use of the vGPU device as if they are in a natively physical machine. In this way, the GPU, a physical GPU, can be shared between different ports of Kubernetes. To each of the worker node, it feels like it has a full GPU device. In fact, the GPU device of the worker node is a fraction of a physical GPU. For example, in the purple ones, it's a GPU is like a half of a physical GPU that's mapped into each of the VM. And the green ones, each of them is a quarter of a physical GPU. The computing power is a quarter of the GPU. So in that way, each of the VM will have a portion of the physical GPU internally. So essentially, it's sharing the GPU for the physical GPU for the workload. Next, I will talk about how to make use of this GPU in Kubernetes. So there's still a little bit more setup that's required in the Kubernetes. So I'll let Zhang talk about that and show a demo after it.
Yes. Well, after we know we have a requirement for GPU sharing. So now I will introduce how to use the virtual GPU in Kubernetes. Yeah. The first thing is you need to provision the worker nodes with the virtual GPU device and use the device plugin to discover and report the virtual GPU results. And the simple method is you need to label the worker nodes with the different virtual GPU capabilities. And like you see in the diagram, the worker VM 1 and 2 are consuming with the virtual GPU with 8 gigabytes frame buffer, which is a half of a physical GPU. So we label worker node 1 and worker node 2 with vGPU dot type equals 8 GB. So same as the worker VM 3, 4, 5, and 6. You can see here they are consuming the virtual GPU with 4 gigabytes frame buffer. So we used a different label for worker nodes 3, 4, 5, and 6. Yeah. So now you can define the part to use the virtual GPU. Here we use the NVIDIA device plugin as an example. It discovered virtual GPU results like a physical GPU results and report the discovered results to the kubelet. So now in your part definition, you can request the one GPU results and to specify how much GPU results you want to consume using the node selector. In this example, you can see we want to deploy a pod to a node with 8 gigabytes frame buffer, virtual GPU. And as even though you request one GPU results here, actually it's consuming a virtual GPU with it's consume a half of a physical GPU here. And as you know, we leverage the virtual GPU technology, so the QoS and the isolation is provided by default. Oh, let's see the demo. So now we will demo how to schedule a pod to a worker node with a specific virtual GPU device. Yeah. Yeah. Let's show what's the current Kubernetes cluster setup here. Yeah, you can see here we have 2 worker nodes with a different label information. Now we can get more details for these 2 worker nodes. This is the worker node 0. Yeah, you can see here we have a GPU resource, and yeah, the labels include the virtual GPU profile. Here is the 4 gigabytes frame buffer, and let's see the next worker node. Yes, you can see here, we use a different label. This worker node has 8 gigabytes frame buffer. Let's go to the each worker node to check the specific virtual GPU profile. Yeah, you can see here 4Q and 8Q. Yeah, this is the Tesla type for NVIDIA virtual GPU device. Yeah, let's deploy a TensorFlow pod to a worker node. Yeah, let's see the pod. Oh, here we need to monitoring the virtual GPU here. You can see later you can see that there will be 1 container to consume the virtual GPU later. Yeah, let's see the pod YAML. Yeah, you can see here we request the 1 GPU resource and specify the node selector to consume the 4 gigabytes frame buffer. You know, the pod will be scheduled to the first worker node. Yeah, it's running. You can see here there is a process on the worker node worker node 0, and this is a 4Q Tesla 4Q GPU virtual GPU type profile. Yeah, that's done for this demo. Yeah, you know, this is just a simple demo to consume the virtual GPU using the node selector. But actually, we can provide a more flexible method to consume fractional GPU. We can extend the scheduler and change the device plugin. Yeah, we change the device plugin to discover and report the virtual GPU. You know, due to the restriction of API server, the fractional number is not allowed. So we use 1,000 to represent a physical GPU. And for example here, you can see we report a virtual GPU resource as a number 500. So that means we discover a virtual GPU with half of a physical GPU. So here we report 500. And next, we extend the Kubernetes scheduler to support the new resource type, virtual GPU resource type. And we use the filter and the prioritize method to select the best matching worker node. And we use the bind method to deploy the part onto a worker node. Yeah, and we also need to add the annotation into the part definition file about the requesting virtual GPU results. Yeah, and the kubelet will use this annotation to update the worker nodes with the virtual GPU usage with the virtual GPU to update the virtual GPU results correspondingly. Yeah, this code is under development. We will open source it later. In next page, Harry will introduce the user case for virtual GPU. Okay, thanks.
So one more thing is that just now we introduced a way to have a fractional GPU because we don't want to change the upstream code. So we use 1,000 as one whole CPU and then use 500 as a half of a GPU. So that by customizing the device plugin as well as extending the scheduler, we can achieve a way to fractional GPU. So it's more easy for the actual use. So next, I want to cover two of the use cases that for this GPU sharing techniques. The one thing I want to talk about, the first thing I want to talk about is the traffic case. I'm coming from Beijing. I'm based in Beijing. So in Beijing, in the city, there are many cameras on the roads that are monitoring the traffic daily. So if a car is on the road with its insurance expired, the camera will capture this vehicle and then will generate a notice to the owner of the car and maybe issue a notice for a fine. So or to remind the owner to be to buy some insurance up to date, right? So for each of this work to be working, we need to have the identification of each of the car image. So in this sample, it's virtually becoming a image recognition problem. So for each of the car we identify, we outline the box of this car and then send it to an inference server for it to capture the license plate to know the car's license number, and then based on that we'll check whether it has the insurance expire or not, so that we can decide whether to issue take any action. So this works pretty simple, right? But what happens when there's many cars on the roads? You are having a concurrency problem, right? So you have many cars that you need to identify at a certain time. So what do you do? So one way is that if you're still using one inference service, that you will have a bottleneck instantly on that inference service. Every request will go into that bottleneck, right? And we could use the scale it out, use multiple instances of inference services. In that way, each of the image recognition work will be used or will be handled by the additional inference services using GPU. So virtually, we are sharing the physical GPU by multiple threads or by multiple requests serving at the same time. So we can increase the utilization of the physical GPU. This is a very common use case for inference service, especially for inference service, the virtual GPU is useful for that purpose. You can scale out as needed, and also we can shorten the response time so that you don't need to worry too much about having a lot of hardware there for the very expensive hardware. That's one use case. The second use case I'm going to talk about is actually a university in China. They have a very diverse workload, machine learning workloads in a very large cluster for a large group of students, faculty members. And they're doing research work, teaching, development, all kinds of different workloads, and training, inference, data processing, all kinds of workload together. So by using the virtual GPU, we can allow those people to share the machine learning workload on top of the same cluster, physical cluster. So we can increase the utilization, increase density, and have multi-tenants and software-defined policies. So for example, like here, in the daytime, the physical box can be shared by 4 different people for different workload. And for example, for development of a distributed training, or you can for teaching or learning purposes. And at night or the nighttime, we don't need that much users. Then we can have to have the to remove all those or suspend all the daytime worker nodes, and then replace by a relatively larger virtual machine or worker node, so that you can make use of the full power of the physical GPU. In that case, that all the training, heavy GPU intensive workload like training can happen in this very bigger box. And also all this process switching back and forth can be done by using automation script or other API calls that we can achieve this goal. I will let Zhang again to have a demo for how we can switch the profiles between different worker nodes so that you understand how actually they're helping the people to have a flexibility in their configuration.
Yeah, let's assume we only have one host which has GPU device.
Yes.
Yeah, here we have a deploy 4 worker nodes on same ESS on same host with 4 gigabytes frame buffer. Yeah, let's check the Kubernetes cluster. Yeah, you see here we have 4 worker nodes. Yeah, let's go to the worker nodes to see the what your GPU profile. Yeah, just take 2. For example, yeah, you can see here we use the 4 gigabytes. Yes, here it's also a 4 gigabytes virtual GPU profile. So let's suspend the worker nodes 0 to 4. Yeah, this is a simple script to automate suspend the worker nodes. And you can see here, you can specify the label which you want to suspend. So our virtual VMs will be powered off. Yeah, let's see the Kubernetes, see the currently Kubernetes setup. You can see our worker nodes, yeah, our worker nodes are not ready. So let's start a new worker nodes which consume the whole physical GPU. Yeah, in our demo, the whole physical virtual GPU is Tesla V-100 with 16 gigabytes. Yeah, let's check the Kubernetes setup. Here, there is another worker node is ready. So let's go to the worker node to check the worker node is using a physical GPU. Yeah, this is the worker node 5. You can see here it's consuming a whole physical GPU. Yeah, this is just a simple demo for the user case too. You can deliver your own script to suspend and resume the worker nodes which you want to do. Okay, thanks.
Yeah, so that's a very simple demo, very fundamental, but I hope you get the idea about how we can share a GPU between different ports, worker nodes, so that you can share workload, especially useful in the cases that like inference service, you can have different services sharing the same physical GPU. And basically, Kubernetes is suitable for machine learning workload. And using our techniques in the GPU virtualization for the machine learning workload, we can achieve a few benefits, like utilization will be very high, relatively high. You don't have idle, less idle physical devices because GPUs are expensive. And also you can have better scalability. You can have more concurrent different workload or mixed workload. You can have handle more requests at the same time. And also you can have isolation and QoS because many of the existing solutions in the community, they don't have this isolation and QoS property. Also, one more thing I want to talk about is the suspend. We can suspend a virtual machine along with the vGPU and also resume at a later time. Also in VMware, we can do the live migration. Instead, you can move the workload from one place to one machine to another machine. That means that you can have a better maintainabilities because when you need sometimes for maintenance, you can migrate the workload to another physical box without stopping your current training job. And also we can have snapshot and cloning, all those kind of things are coming from the virtualization, either from CPU or GPU. So with that, all this is our idea of the GPU sharing on Kubernetes. So by taking advantage of the virtual GPU technologies. I hope you get the idea. Again, this is simple and introductory, but I hope you get the idea and then you can utilize it to more interesting work based on our introduction here. So that's all what we have so far. Thank you, and if any question, I'll be happy to take some. Zhang, you can keep the microphone.
Thank you. It's interesting stuff. How do you decide whether you want to just use the virtual GPU API versus switching out your worker node to have a smaller GPU or bigger GPU, like suspending it and starting it again?
Sorry, I didn't get the question. So Yang, you go.
Oh yeah. So how do you decide between just using the vGPU API that you can create in Kubernetes versus suspending and recreating the node with a different size GPU? Like when should you do that? Like why do you even need to do that?
So the question was how do we decide when to switch the different profile of the GPU, right? vGPU. So sometimes depending on the workload actually, so like in my example there, before when we have 4, we need to split into 4, like for example 16 gigabyte, each have 4 gigabyte for smaller jobs, machine learning jobs, right? If you have smaller than you don't need the full power of the GPU, you can have smaller one.
Oh, maybe I'm missing. Maybe I didn't describe it. So, the vGPU API allows you to dynamically request it on the worker nodes that exist, right? So, like I can deploy a pod that has 500 units, and then it uses half of the GPU. Why do I also it also made it seem like you have to actually shut down the node to change the size of the GPU.
So your question is why we need to suspend some worker nodes and to resume some worker nodes? You mean the pod can consume a specific virtual GPU resource in our demo, right? That was because for the hypervisor, for the hypervisor, if we only have one host with GPU with physical GPU device, for the hypervisor we cannot flexible to specify which virtual GPU you want to use for your VM. So if you use one virtual VM on the physical host to use a virtual GPU profile like 4 gigabytes frame buffer, you cannot deploy a 8 gigabytes virtual VM onto the same host. So that's why if you want to deploy a new worker node with a different virtual GPU device onto the same host, so we need to suspend the existing VM and resume a new one. I'm not sure if it's your question.
Yeah, I mean the reasoning is that when you assign 4 VMs here, you already assign all the video buffer, the memory buffer of the GPU card. So you cannot spend another VM that reusing this, sharing this same physical GPU. So we need to shut them down before we release the GPU resource and then reorganize as one big host of the VM. That's why. Hopefully that answers your question. Okay. Any question?
Yeah. I'm seeing this virtualization of the GPU, and I'm wondering if this is specifically for the case of multi-tenancy Kubernetes deployments, where you maybe create one cluster of Kubernetes for each tenant, and you don't want that the different nodes, computes of the different Kubernetes cluster share the same GPU, so you create a virtual GPU and a virtual machine. But for single tenant, this is not needed, as I understand. No, because
for single tenant, there's also a use case. I mean, I know your question is that if you have multiple tenants, you do want to separate them, right? You isolate them. But for single tenant, there's also a use case for the noisy neighbor. Even the same tenant will have different jobs. They can, if you don't have isolation, then you can need to interfere with each other. Then you cannot guarantee which one will work better, which one will finish first. It's hard to guarantee that.
But you can assign a fraction, even in the case of.
So if without the GPU technology, vGPU technology, all the workload will be scheduled together. So you cannot guarantee which one gets how much share of the physical GPU.
Then what's the meaning of the fraction part? If you assign a fraction but you cannot enforce it?
No, there's no fraction. Fraction only works on our vGPU. Without our vGPU technology, the fraction thing doesn't work.
So the fraction you describe in the pod refers to the partition in virtualized mode, not in the usage of each virtual GPU.
Sorry, I didn't get the question.
So the meaning of the fraction number is regarding not the fraction inside a virtual GPU, but how
the fraction thing is a way. So without the fraction thing, we rely on the node selector to assign the actual physical GPU resource, the virtual GPU resource. This fraction thing is that we want to make it more flexible or convenient for the user to assign to request the resource they want. It's not just for isolation. It's for if I can only use a half of a GPU, or if I can use a quarter of a GPU, that's by this number. So by some customization of the Kubernetes code, device plugin, and the scheduler.
Okay, thank you.
Okay. There's one more at the back.
So for this fractional allocation of devices, isn't it so what you will get 500 allocate calls in your device plugin?
About 500 what, sorry?
So for each instance, like for each single digit in your resource request, you will get the allocate call to device plugin. So if you're requesting, let's say, like in this pod above, like 300 vGPUs, you will get in your device plugin 300 allocate calls.
Yeah, this 300 is we deliberately make it not exactly the same as 500. So for here, for this device plugin, it reports 500 because it is a half of a physical GPU like here. This physical GPU has been divided into two right, identical ones. Each of them is actually a half of a physical GPU. And then it mapped into the worker node as a one GPU, right? It's in the worker node.
But
and then we report it.
Kubelet will 300 times call the plugin allocate me device.
I'm sorry?
The kubelet will 300 times call the device plugin saying allocate me.
No, it's not 400. We modified it. So you report it to the kubelet is 500, right? 500. And then when we're doing the allocation, we deduct 500 directly. It's not, we do not deduct 300. Okay, you mean the allocation is 500? Have what? Sorry.
If you overload API.
Overload the API? I think it's overload. It's one call, right? It's not 300 times calls, I guess. 100 calls? It means 300 calls, you mean?
If you track the status of this GPU.
Okay. 500 times? Okay. So that's the way we're trying to simplify the API. And I know what you mean. Yeah. So we need to verify that piece. That we are not quite sure because we're in a process of making this working. We haven't reached the final step, but the idea is that we don't want to change the code for the Kubernetes API server, so we reuse the integer number there. But if you think it's avoiding the 300 calls, right? You think 300 calls? For 1,000, sorry, what? Okay, API calls too many, right? So we need to find a way to get around with that. So I understand what you mean. You incur many costs there?
Yeah, I have another question about, does it work only for one physical GPU? This implementation of fractional GPU, does it work for physical?
Yeah, right, you're right. But we do it in assumption that we only have one GPU, physical GPU.
So only one GPU, you should have only one physical GPU, right?
Yeah, the assumption right now is one vGPU. Yeah, we still have to improve it, but not yet that far yet.
You mean you have 4 physical GPU, for example, right here. So you want to schedule your part to a physical GPU. Maybe more flexible. You want to schedule or virtual GPU or physical GPU, right? Oh yeah, Kubernetes can we can enhance the device plugin. The device plugin to schedule the part to a specific GPU. But I mean, we only support one virtual GPU per virtual machine. If you want to pass through the part, you want to use more than one GPU per part, more than one physical GPU.
Right now there's a limitation that you cannot have 2 fractional virtual GPU inside one VM. That's currently, we are working on that, whether we can.
What's the...
And does it work in KVM?
KVM may have a different way to work it out.
Have you tested it?
We haven't tried that, but we just tried it on vSphere for now. Yeah, but KVM may have a different mechanism to work. But the idea here is we present here is to try to making the fractional number working. Okay, I think that's all. Now, thanks for coming for this session, and this is the last one. Thank you very much.